Right now, at this exact moment, there's a spacecraft in interstellar space carrying an instrument that its twin lost almost half a century ago. Not a backup, not a redundant system. The single instrument that turned out to matter most at the edge of the solar system, still working on one spacecraft, dead on the other. And that difference changed everything scientists thought they understood about where our sun ends and the galaxy begins. Everyone knows Voyager 1, the farthest human-made object ever built, the spacecraft that crossed into interstellar space in 2012 and has been making headlines ever since, the one with the golden record, the one every documentary opens with. But Voyager 1, for all its fame, was blind at the exact moment it mattered most. It crossed the most significant boundary in the solar system without the ability to directly measure the very thing that boundary is made of. And it was Voyager 2, quieter, less celebrated, arriving 6 years later from a completely different direction that did something Voyager 1 physically could not do. It measured the plasma, on both sides of the boundary, at the same time, for the first time in the history of human spaceflight. And what it found did not confirm the story Voyager 1 had been telling for 6 years. It rewrote it. Voyager 2 launched on August 20th, 1977, 16 days before Voyager 1, and despite carrying the higher number, it was never the backup. It was given a longer, more complicated route, one built around a rare alignment of the outer planets that happens roughly once every 176 years. That alignment let Voyager 2 do something no spacecraft before or since has managed. It visited all 4 giant planets, Jupiter, Saturn, Uranus, Neptune, one after another, using each planet's gravity to sling itself toward the next. Voyager 1 took the faster path, past Jupiter and Saturn, then out of the plane of the solar system entirely, trading Uranus and Neptune for a closer look at Saturn's moon Titan and a quicker route to the edge. 2 spacecraft, 2 different answers to the same question. What does the far edge of our solar system actually look like? The price Voyager 2 paid for seeing all 4 planets was time. Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, in August 2012. Voyager 2 didn't cross it until November 5th, 2018, more than 6 years later. For those 6 years, Voyager 1's data was the only data anyone had from beyond that boundary, and it was already forcing scientists to rebuild their models. But the story from Voyager 1 was incomplete in a way that almost never gets mentioned when people talk about what it discovered. Its plasma science instrument, the device built to directly measure the temperature, density, and flow of plasma both inside the heliosphere and beyond it, had degraded so badly that engineers formally shut it down in 2007, decades after its usefulness had already faded. When Voyager 1 crossed the heliopause in 2012, it crossed the single most important boundary of its entire mission without a working plasma detector. Scientists could infer conditions from the cosmic ray subsystem, the magnetometer, the plasma wave instrument. They could not measure the plasma itself. They were working around a hole in the data that had existed for years, and there was no way to fill it after the fact. Voyager 2's plasma instrument was still alive. When it crossed the heliopause on November 5th, 2018, it carried a functioning sensor that Voyager 1 had effectively lost before either spacecraft had even reached the halfway point of its mission. And that instrument, at that boundary, produced something researchers would later call historic: the first direct simultaneous measurement of plasma on both sides of the heliopause, taken as the spacecraft physically crossed from the solar wind into interstellar space. Not inferred, not modeled. Measured directly, in real time, by an instrument still working after 4 decades in deep space radiation. 5 papers were published together in Nature Astronomy in November 2019, describing what that instrument found. And what it found didn't just add detail to Voyager 1's picture. It contradicted parts of it and complicated the rest. The first surprise was about the shape of the boundary itself. Scientists expected the heliopause to be thin and sharp, a narrow line a few 100,000 kilometers wide, where hot solar wind met cold interstellar plasma, and the two blended briefly before separating cleanly. Voyager 2 found something else entirely, a transition zone, roughly 100 million miles wide, sitting just outside the boundary, in territory that was supposed to be pure interstellar space. Instead of a clean edge, there were tendrils of interstellar material pushing inward, mixing with the solar environment in ways no model had anticipated. Voyager 1 had glimpsed something similar on its own approach, a region where the outward-moving solar wind had slowed nearly to a stop just before the boundary. But the 2 spacecraft, crossing at different points 6 years apart, described genuinely different structures. 2 crossings, 2 boundary shapes, same solar system. Then there was the distance itself. Voyager 1 crossed the heliopause 121.6 astronomical units from the Sun during a period of high solar activity. Voyager 2 crossed it at 119 astronomical units during a period of low solar activity, Scientists expected the heliosphere to expand and contract significantly with the solar cycle, growing larger when the sun was active and shrinking when it was quiet. Instead, both spacecraft found the boundary in almost exactly the same place, regardless of what the sun was doing. Stamatios Kremigis, a principal investigator on the mission at the Johns Hopkins Applied Physics Laboratory, said it plainly: they didn't understand why. Not as a passing caveat, but as a direct statement from someone who had spent decades with this data that something fundamental about the relationship between solar activity and the size of the heliosphere didn't work the way anyone's model said it should. The second major surprise was temperature. And this is where Voyager 2's working plasma instrument mattered most, because temperature in plasma physics is measured by how fast particles are moving, and that measurement was something Voyager 1 simply could not provide. Scientists expected a sharp drop in temperature at the boundary from the extremely hot, fast-moving solar wind plasma to the colder interstellar medium outside. Voyager 2 confirmed the drop was sharp, sharper than predicted, but it also delivered something new, a direct reading of interstellar plasma temperature, something that had only ever existed as a theoretical estimate before. The measurement came back at 30,000 to 50,000 degrees Kelvin, warm by everyday standards, but far cooler than the tens of millions of degrees measured. Just inside the boundary, the previous theoretical estimate had been off by roughly a factor of 2. That's not a rounding error. That's a fundamental correction to a number the entire field had been building models around. The third surprise, and the one Voyager project scientist Ed Stone called the most remarkable, was that the boundary leaks, not metaphorically. Literally, particles cross it in both directions. Voyager 1, approaching from one side, detected tendrils of interstellar, particles pushing into the heliosphere from outside. Voyager 2, approaching from a completely different angle 6 years later, found something different but related, a trickle of low-energy solar particles leaking outward into interstellar space before the spacecraft had even reached the boundary. 2 spacecraft, 2 different entry points, 2 different mechanisms. The same underlying conclusion. The heliopause isn't a wall, it's more like a coastline, with material moving across it in both directions at once. Stone's own description of it captured how significant that shift was. Not a line where the sun ends and interstellar space begins, but a continuous, dynamic interaction between 2 environments that refuse to stay cleanly separated. None of this would have been knowable, or at least knowable with this level of certainty, from Voyager 1 alone. Now that's the part of the story that gets lost. Voyager 1 gave humanity its first taste of interstellar space, and that achievement is real and enormous. But the specific physical measurement that turned 6 years of inference into 6 years of confirmed, contradicted, and refined science, the thing that let researchers say for the first time what interstellar plasma actually is, rather than what it was theorized to be, came from an instrument that only existed, still working, on the second spacecraft. This wasn't an accident, and it wasn't luck either, not entirely. The Voyager mission was designed in the 1970s by engineers working with computers less powerful than a modern calculator, and they built a 2-spacecraft mission specifically because one data point can never tell you if what you're looking at is typical or unusual. 2 spacecraft approaching from different directions at different times can start to build an actual picture instead of a single snapshot. What they couldn't have fully planned for was that the single most critical instrument for understanding the crossing, the plasma detector, would fail on one spacecraft decades before the mission's biggest moment and survive, against every expectation about component lifespan on the other. The division of labor between the 2 spacecraft was intentional. The specific way it played out, with Voyager 2 quietly carrying the instrument that filled the gap Voyager 1 left behind, was not something anyone could have guaranteed in 1977. Now, bring this forward to today, because the story doesn't end with the 2019 papers. It's still unfolding right now in the summer of 2026, and the stakes are different this time. They're not about what these spacecraft can discover anymore. They're about how much longer they can keep discovering anything at all. Both Voyagers are powered by radioisotope thermoelectric generators, devices that convert heat from the steady decay of plutonium-238 into electricity. That decay is mathematically certain and cannot be stopped, slowed, or reversed. Each spacecraft loses about 4 watts of available power every year, a number that sounds small until you remember that each spacecraft started with roughly 470 watts total and has been losing ground every single year since 1977. For most of the mission, the response to this decline was the same: turn something off, one instrument at a time, in an order the science and engineering teams agreed on years in advance, sacrificing capability to buy years of remaining life. That process has already claimed most of each spacecraft's original 10 instrument sets. Voyager 2's plasma science instrument, the very instrument that made the historic 2018 heliopause measurement possible, was itself powered down in late September of 2024, Not because it had failed, but because its usefulness had diminished with the spacecraft's orientation and its power draw, could no longer be justified against the alternative of keeping other instruments alive. Voyager 1's cosmic ray subsystem went dark in February 2025. Voyager 2's low-energy charged particle instrument followed in March 2025. Then, on April 17, 2026, engineers at NASA's Jet Propulsion Laboratory sent the command to shut down Voyager 1's own low-energy charged particle experiment, an instrument that had been running almost continuously since 1977, nearly 49 years of uninterrupted operation, gone in a single afternoon of commanding from a control room 13,000 miles from the spacecraft it was talking to and roughly 23 hours from the spacecraft, in terms of how long the signal actually took to arrive. As of right now, Voyager 1 is down to 2 functioning science instruments, its magnetometer and its plasma wave subsystem. Voyager 2 still has 3, the magnetometer, the plasma wave subsystem, and the cosmic ray subsystem, though NASA has already said that instrument is scheduled to be shut off later this year. Every one of these decisions was made years in advance by a team that sat down together and planned, in order, exactly which pieces of these machines would go dark and when, trying to keep the most scientifically valuable instruments alive the longest. There's no improvising this. There's no emergency repair crew. There's a schedule built out of hard trade-offs, and it's being executed one command at a time across a distance that makes every single decision permanent the moment it's sent. But there's one more move left, and it's the reason this particular summer matters more than any other in the mission's recent history. NASA calls it the Big Bang. The idea is to swap a whole group of powered devices on the spacecraft simultaneously, turning off higher power systems and replacing them with lower power alternatives in an attempt to squeeze back some of the efficiency the aging power system has been losing. Rather than making these changes one at a time, testing and verifying each step before moving to the next, the entire reconfiguration happens at once. The reasoning is about risk. Every power system change creates a transitional moment where the spacecraft is neither in its old configuration nor its new one. And those in-between moments are exactly when a spacecraft's automated fault protection systems are most likely to trip, cutting power to components on their own if they sense a draw the generators can't support. The whole point of doing it all at once is to get through that dangerous transition as fast as possible instead of lingering in it. If it works, engineers believe it could buy at least a year of additional operating life for the spacecraft's science instruments, possibly more. There is even a chance, if it goes well enough, that Voyager 1's LECP instrument could be switched back on, which is why engineers made the unusual decision to leave a small stepper motor inside that instrument, running at roughly half a watt, just in case, even after shutting the rest of it down. Voyager 2 is going first, not because its data matters less, but because it currently has slightly more power margin and is closer to Earth, meaning a shorter, though still enormous, communication delay of around 20 hours each way compared to roughly 23 hours for Voyager 1. That makes it the safer test subject for a procedure that has never been attempted before, at this distance, on hardware this old, with no way to intervene once the sequence begins. Tests are running through May and June of 2026. If they succeed, and only if they succeed, engineers plan to attempt the same maneuver on Voyager 1, no earlier than July. Everything Voyager 1 might gain this year depends entirely on whether its twin survives this procedure first. Think about what that means. The spacecraft most people have never really focused on, the one that quietly did something its more famous twin never managed, the one that carried the plasma instrument that rewrote. The science of the heliopause is now the one whose survival determines what happens to the far more famous Voyager 1 later this year. Voyager 2 isn't in Voyager 1's shadow anymore. For a few critical months in 2026, Voyager 1's future runs through it. And there's a deadline layered underneath all of this. Voyager 1 is expected to cross one light day from Earth in November 2026, a distance so vast that a radio signal traveling at the speed of light takes a full 24 hours to cover it. That milestone arrives right around the spacecraft's 49th anniversary, with its 50th year in flight, approaching fast. Every watt the Big Bang can recover is a watt that might carry these instruments across that milestone, still transmitting, still returning data from a region of space that no other operating spacecraft currently occupies and won't for decades, because there is no successor mission out there right now. New Horizons is heading outward too, but it will take a very long time to reach comparable distances, and nothing else humanity has built is anywhere close to the interstellar medium these two machines are already sitting inside. The team doing this work is small, and it has always been small. Many of the original Voyager engineers have retired, and the people who replaced them had to learn spacecraft conventions and command protocols from an era that predates their own careers just to keep talking to machines that were designed before the internet existed, before GPS, before personal computers, or common household objects. That knowledge doesn't live in a modern engineering curriculum. It lives with a specific group of people at a specific facility, and every year that group gets smaller right alongside the power budget they're managing. What's actually at stake here isn't just extending a mission for its own sake. It's the questions the 2019 findings raised but never fully answered. Why does the heliopause sit at almost the same distance regardless of the solar cycle? What's actually driving the leakage of particles across the boundary in both directions? Does that leakage change as the sun moves through different regions of the galaxy? What shape does the heliosphere actually have? A long tail trailing behind the sun's motion through the galaxy, a rounder bubble, something in between. Voyager 1 and Voyager 2 are sampling two different points on that structure right now, one closer to the nose, one further toward the flank. And every additional month, either spacecraft stays alive, adds another data point to a picture that has no other way of being built. There is no telescope on Earth or in orbit that can substitute for a physical instrument sitting inside the interstellar medium. When these two machines finally go silent, whenever that happens, the map they've been building simply stops. It won't resume until some future mission, not yet designed, not yet funded, not yet launched, eventually makes the same 40-plus year journey and arrives at the same boundary decades from now. Voyager 2's full list of achievements is almost too long to hold in your head at once. The only spacecraft ever to visit Uranus, discovering 10 new moons and 2 new rings during its January 1986 flyby, and measuring a magnetic field so wildly offset from the planet's rotation axis that it still challenges how scientists think planetary magnetic fields form. The only spacecraft ever to visit Neptune, finding 6 new moons in August 1989, including one so large it probably should have been spotted from Earth long before Voyager arrived, and clocking supersonic winds of 2,400 kilometers an hour, the fastest ever measured anywhere in the solar system. It found active nitrogen geysers on Neptune's moon Triton, shooting material kilometers into a thin atmosphere, and helped confirm Triton was almost certainly a captured object from the Kuiper Belt, rather than something that formed in place. It returned the first close images of Europa's cracked, reddish-streaked ice, images that seeded decades of scientific interest in the possibility of a hidden ocean beneath that surface, and eventually helped justify an entire follow-up mission built specifically to study it. Right now, tests are underway on Voyager 2, 13 billion miles from Earth, in an attempt no one has ever tried at this range, on hardware this old, with a procedure nicknamed for how completely irreversible it is. If it works, the spacecraft that quietly did, all of that from a spacecraft launched on August 20th, 1977, designed to operate for 4 years, still returning data 49 years later because of a route nobody else has ever repeated, and an instrument that happened to survive exactly long enough to matter. Right now, tests are underway on Voyager 2, 13 billion miles from Earth, in an attempt. No one has ever tried at this range, on hardware this old, with a procedure nicknamed for how completely irreversible it is. If it works, the spacecraft that quietly did what its famous twin never could gets more time to keep doing it. If it works, Voyager 1 gets its own shot in July. If it doesn't, the schedule that was supposed to carry these two machines toward their 50th year gets a lot shorter all at once. Every command in this test takes roughly 20 hours to arrive and another 20 to bring back an answer. Every diagnostic step costs the better part of 2 days just in travel time for the signal alone. And through all of it, a small team at JPL keeps sending commands into the dark, awaiting for replies that are already old by the time they land, still trying to keep two 49-year-old machines talking from a place nothing else built by humans has ever reached. Consider, too, how strange it is that this all still hinges on decisions made half a century ago. The engineers who chose Voyager 2's trajectory in the 1970s couldn't have known which instrument would fail and which would survive. They only knew that sending two spacecraft in different directions gave humanity a chance no single mission could offer. Nearly 50 years later, that choice is the reason anyone has direct physical proof of what interstellar plasma actually is, rather than a number pulled from theory. That's the part of this story worth sitting with. Not just what was found, but how close humanity came to never finding it at all. The result of the Big Bang test on Voyager 2 is coming. The attempt on Voyager 1 in July is coming. The one light day milestone in November is coming. When those moments arrive, you'll want to already understand exactly what you're watching and why the two spacecraft nobody talks about turned out to be the one holding the whole mission together.